All right, folks, let's do number 29. A train slows down as it rounds a sharp horizontal turn, slowing from 90 kilometers per hour to 50 kilometers per hour in the span of 15 seconds. That it takes to round the bend. The radius of the circle is 150 meters. Compute the acceleration at the moment the train reaches 50 kilometers per hour, assuming it continues to slow down at this time at the same rate. All right, folks, so what's going on? So you have a circle. Now I'm going to do a little tradition here, or not tradition, but like I'm going to pick my own direction for this problem. So realistically, you could put any pathway you want. It doesn't have to be start at the angle at the horizontal where equals 0. In fact, trigonometry states specifically, or mathematics, or the applied physics states, and this is why I love the material so much, is that you can pick whatever direction you really want. So I'm going to do exactly that. I'm going to pick the direction, not here, but I'm going to start it at this point, and I'm going to define the angle to be 0 at this radius. Can you do that? Yeah. I mean, this is mathematics after all. So who gives a fuck? So I'm going to define this to be a radius. That radius is going to be 150 meters. And the A tangential, and let me move this. So you're going to have the tangential velocity right here at some direction. You're going to have A radial is going to be right here. So here you're going to have A radial. Here you're going to have the velocity, and that velocity is going to vary. So, and you're going to have the A centripetal right here. So there's going to be A tangential right here. This is what's going to make the velocity. That is going to change the direction of the velocity. So you can see that the magnitude here between these components is this. Now this is going to be starting at that point. So what I'm going to do is I'm going to find the final speed that this takes. So let me reach. So let's say that here you have A radial right here. Let's say it ends at this point. We don't know exactly where, but let's say that this is going to be A radial. And let's say that A tangential is going to be some speed that's going to be slowed down at some final speed. So that's going to be V. And let's say that this is going to be A tangential. So let's calculate what A radials is. And keep in mind, folks, the radial acceleration when it's slowing down realistically always changes. So it's never going to be a constant value, especially when you have a acceleration. So in order for this to be a circle, the A radial would have to be a specific value in order for this to work. So you could still model the motion, but you definitely have to take that into the account. So A radial is going to be the speed. Now, what speed? What is the speed? Notice that I'm going to define that to be the final speed when it reaches 50 kilometers per hour. So it's not change of speed, it's the final speed. So I'm going to take the final speed as 50 kilometers per hour. I'm going to take the initial speed to be 90 kilometers. Oh, I guess it was faster. I don't know. I'm not really paying attention. But so the acceleration the velocity was much higher in magnitude, and then it slowed down. But it's perfect because I did put it in the opposite direction, so it's fine. So we're going to say that this is going to be the final speed at 50 kilometers per hour square divided by the radius at 150 meters. The question is asking the radius, compute the acceleration the moment the train reaches at 50 kilometers per hour. But notice that we are just talking about the A radial component. I hope you guys catch that, because the question is asking for compute the acceleration at the moment. So it's not just talking about A radial here, but it's also talking about the A tangential component. So what's the A tangential component? A tangential is going to be the final velocity minus the initial velocity over the time interval it took, which this case is going to be 15 seconds. So 15 seconds. So I'm just going to put t. You could put t minus t now. It doesn't really matter. That's it, folks. It's just plugging and chugging at this point. So I'm going to take 50, store 50 kilometers per hour, 10 to the 3 divided by 60 square. Store alpha v. And 150 meters, store alpha r. V squared over r is going to be some value where a radial is going to be 1.29 meters per second square, and a radial or a tangential is going to be what's that, 40 times 10 to, okay, so I'm going to convert that. You could keep it as kilometers if you want, it doesn't really matter. So I'm going to divide that by 15. So the A tangential is going to be 0.74 meters per second square. Now let's compute the final acceleration. Now I'm going to use the Pythagorean theorem, folks, because remember that this is going to be that square plus a tangential square. So the magnitude of the acceleration is going to be a radial square plus a tangential. So I'm just going to do nothing more than to plug and chug these values. And I didn't mess up on the other video, so I forgot to take the square root on the other one. but the magnitude for this one is going to be 1.48 meters per second square. And remember, that magnitude is going to be this component. So anyways, folks, I hope this helps.